This month's practical chemistry focus, we are going to look at clock reactions and how we use them in rates of reaction experiments to find out orders or to find out activation energy by changing temperature. So before we get into what a clock reaction is, let's talk about what it isn't. What's the opposite to a clock reaction? So most of the time when we first started doing reaction rates experiments, we should know that all rates require us to monitor the change in reactant used up or the change in the product made over time. So a really simple example of that, which you probably even did at GCSE, would be measuring the volume of gas maybe every 20 seconds when a metal reacts with an acid. And that's an example of continuous monitoring. So we're taking continuous readings over time. We can follow the reaction until the end, and we end up with a graph that looks like this. We could change the initial conditions, so there are two lines on this graph. Maybe line B is happening at a lower temperature, at a smaller surface area, or a reduced concentration. We can see from this graph just by eye that line B is slower than line A. We can also see though that both of these are curves, and the reason that these graphs are giving us a curve is because we're following the reaction all the way to the end, which means that the concentration of whatever it is, in this case acid, is decreasing over time, and therefore the rate is slowing down, and then eventually we're using up all the acid and the reaction comes to a stop. And we could use this continuous monitoring method. We could find the rate at any particular point by drawing a tangent to that curve and then calculating the gradient, in this case volume of gas, over time. And we can see that that gradient is changing. So we could actually take maybe 5 different tangents off this curve, and then we could plot a graph that would show how that decrease in concentration affects the rate of the reaction. So we could also use this continuous monitoring to work out the orders if we wanted to, because we can see how concentration over time affects the rate. Okay, but that's actually a long-winded method. We could also use the initial rates method, which is far more common if we want to find the order with respect to a particular reactant. So to find the order, we need to compare the rate of reaction at different concentrations. So for example, we may have done 2 experiments, and in this case, then one of the experiments, like line B, is 0.1 moles per dm cubed, and the other one is related to 0.2 moles per dm cubed. So we can use this graph to find the order. We've doubled the concentration. We're going to find out what happened to the reaction rate. However, this graph is curved, so we can't just find an average rate, because the rate is slowing down as the concentration of the reactant is decreasing. So what we mean by initial rates is that we are only going to consider the very first part of the results table, where the graph is still a straight line. There are then 2 different ways that we could quite easily compare the rates between the 0.1 and the 0.2 molar results. So the first one is that we've got our 2 different concentrations, we've got our results. So instead of plotting this massive old graph that we've done there, we could have just said, do you know what, I'm just going to count 20 seconds on my stopwatch, and at 20 seconds I am going to determine the volume of gas that is produced. So in our 0.1, that's the lower line, seconds is on the x-axis. So I'm just going to read up, I'm going to read across, and I haven't done those lines particularly well, but what I found is that 0.1 moles per dm cubed, the volume of gas in 20 seconds is 19 centimeters cubed. And so to calculate my rate, I can just calculate centimeters cubed per second. So I'll just do 19 divided by 20, and that equals 0.95. And then I could do the same thing again with a 0.2, reading across the volume of gas is about 42 centimetres cubed. 42 divided by 20 is 2.1. Okay, what's the other alternative? So that was fixing the amount of time and measuring the gas produced in that time. Alternatively, and possibly slightly easier, because it's quite difficult, you know, the syringe is not stopping at 20 seconds, you need time to read it. The other option is you watch the syringe continuously and you wait for it to produce a particular volume, and then you're holding the stopwatch so you can immediately stop the stopwatch when you think it's produced, for example, 20 centimetres of gas. So this time I'm going across from the y-axis and reading down, and I find that 0.1, it takes 21 seconds. I'm going to do the same calculation, so it's volume of gas divided by time, so it's 20 divided by 21, which turns out to still be 0.95. And then I can do the same thing at the different concentration, and I can find that it actually takes a lot less time, so it takes 9.5 seconds, and the rate is 2.10. Now, what you should notice is the rates are the same, because I'm measuring this gradient at the start of the reaction, and I'm measuring it at the point when these lines are still straight. So it shouldn't really matter what values I read off. To be honest, at any point during these straight line sections, I can take a value for centimetre cubed and take a value for time, divide one by the other, and for both of those lines they should be the same. And then what I can do is compare the two concentrations. So for this one, when I double the concentration, I'm essentially doubling the rate of reaction. Now, I wouldn't plot this whole graph if this was the method I was doing. I would simply decide whether I'm going to do a fixed amount of time or a fixed amount of product, and I would just wait until that's happened. Now, you can do this either way round, fix the time or fix the product. More commonly, we fix the amount of product and we measure the time taken. And that is the basic, essential method of what a clock reaction is. And you've seen a very simple version of a clock reaction before, also at GCSE, which is the disappearing cross experiment. So that's the reaction for the disappearing cross experiment. You're mixing sodium thiosulfate, which is going to come back later in this video, and acid. It makes a range of products, but the most important thing that it makes in terms of monitoring it is solid sulfur. So as you are doing it, the reaction mixture is going to be kind of turning a cloudy yellow. And then how we monitor that is we put a cross or a mark behind the flask on a bit of paper, and we look through the mixture and we observe the time taken for the cross to no longer be seen. Now, in theory, if we keep all our variables like the volume of reaction mixture and the shape of the container the same, then it should take the same amount of sulfur made every single time for the cross to disappear. So this is like the gas experiment where we were measuring the time taken for a particular volume of gas to be made. This time we're measuring the time for a fixed amount of sulfur to be made. And therefore we can change variables such as concentration of thiosulfate and see how they affect rate. And we can plot a graph. Now, we need to not plot a graph of time because time is not the same as rate. We would have to do 1 over time. And that gives us a value that is proportional to the rate. Now, we could sit there and actually work out rate in sort of moles per second or moles per dm cubed second. It would take ages. We'd have to work out exactly how much sulfur we made, which would probably involve like filtering it out and weighing it. That's just very time consuming. It doesn't matter because the important thing is that I can see from this graph that the concentration of thiosulfate is directly proportional to the rate, and therefore this is a first order with respect to the thiosulfate concentration. Okay, let's get to the real complicated clock reaction, or what seems complicated, the iodine clock. First of all, just the essentials of how we use it. So you can actually use iodine clock method for anything that makes iodine as a product. In this case, most likely to be the reaction between hydrogen peroxide, iodide ions, and acid or H+ ions. But it can be used for other redox reactions, and there are a few small variations where we could also measure things like bromine. So when we mix these things together in a flask, if we were to just mix those three reagents, my acid, my iodide and peroxide, then over time the mixture is just going to go sort of orangey coloured, and then it's going to go darker brown as more iodine is made. So if I wanted to do a continuous monitoring technique, I could do that by using colorimetry because the solution's getting darker and the absorbance increasing, or I could take samples out at different times and titrate those samples to see how much iodine there is, for example, titrating with thiosulfate. And that works because thiosulfate reduces iodine back to iodide, and that's the basis of an iodine thiosulfate titration. However, in an iodine clock reaction, we're not doing continuous monitoring. We're going to do just taking the time it takes for a particular amount of substance to be made. So we've got that reaction. We need to add two other solutions. One is sodium thiosulfate and the other is starch. So to explain what's going on and make it a little bit easier to see what's happening, I'm going to make up some values of moles. They are very large values compared to the real values, but by using these simple numbers, it just helps us see a little bit more what's happening in the experiment. So first of all, I'm also going to say that my total reaction mixture is 1 decimeter cubed, and that means that my moles is the same as my concentration because it's moles per 1 decimeter cubed. That just makes life a little easier as well. Okay, so I did say there were going to be big numbers, so let's say that I've got 10 moles of H2O2 at the start, mixed with 20 moles of iodide ions and 20 moles of H+. And let's say that at that particular mixture, at those concentrations, because it's moles per decimeter cubed, that 1 mole of iodine gets produced every 10 minutes. So that is the rate of production of iodine in that reaction. Now, if we were to just leave it, that wouldn't help me. All I would see is the reaction mixture getting more and more orange and brown as the iodine is made. And there's no way for me to tell by eye that a particular amount of iodine has been made, so I would have no idea when to stop my stopwatch. It's not like the sulfur reaction where I can watch a cross disappear. So I'm going to add to my reaction mixture 1 mole of sodium thiosulfate. So sodium thiosulfate we've come across a few times now. There's that formula. It's really worth learning that formula, the thiosulfate ion, so you're familiar with it. It reacts with iodine in a 2-to-1 ratio. But more importantly, there's a big difference between this reaction and the reaction above. The reaction between sodium thiosulfate and iodine is extremely fast. So it basically is instant as far as we can tell. It takes no time at all. That's why we can use it to titrate to find out how much iodine there is. You can't do a titration with a reaction where you have to wait every time you add something from the burette. You have to wait for it to react. That would not work in a titration. So the top reaction is relatively slow, 1 mole every 10 minutes, and the thiosulfate iodine reaction is instant. So the first reaction is producing iodine 1 mole every 10 minutes. I've got a mole of thiosulfate in my reaction mixture. So in the first few minutes, every molecule of iodine that is being made is reacting straight away with the thiosulfate, and I never see the iodine being produced. So at the moment, my flask looks completely colourless because everything in it is colourless. So that's not going to last, however, because I only added 1 mole of thiosulfate. Now, if we look at the balanced equation, we can see, hopefully, that 1 mole of thiosulfate, it's a 2-to-1 ratio, so that thiosulfate will be used up after 0.5 moles of iodine has been produced. And we know that 1 mole is made every 10 minutes. So my thiosulfate will be used up after 5 minutes under these reaction conditions. So what happens then? Well, if that's all I added, thiosulfate, then what would happen is for the first 5 minutes, no colour, nothing happening. And then after 5 minutes, oh, just a gradual yellow and then a bit darker orange and then brown. And we're back to the same problem we had before. However, remember we added 2 things. We didn't just add thiosulfate, we also added starch. The starch at the beginning, nothing's happening because the iodine is getting used up by the thiosulfate. The moment that 5 minutes is up, my thiosulfate is used up, iodine is released into the reaction mixture and reacts with starch to make a blue-black, very obvious change. So the change is going from colourless to blue-black. I can see it very, very clearly. I know exactly when to stop my stopwatch. I can then change whichever one of these substances I want. The peroxide, the iodide, the acid. I'm going to get a different rate of iodine production per minute, which means it's going to take a different amount of time to produce that same 0.5 moles of iodine. And therefore, I can measure that time taken, do 1 over time to get my rate. So one of the things that's a bit bewildering about this experiment when you carry it out is how many things we're adding and how many different pieces of apparatus and everything else. So normally we have this large table of different volumes of stock solutions as demonstrated here. So I just want to talk briefly about how we design the experiment and why we use different pieces of apparatus each time. So in this particular one, the aim is to change the concentration. So this is my independent variable, my concentration of potassium iodide. So this could be a method of working out the order with respect to iodide ions. Now, if you look carefully and if you've got a good memory for this reaction, in this table we've got sulfuric acid and iodide, which are 2 of the reactants, H plus and I minus. We've also got our starch to use as our indicator for the endpoint. We've got sodium thiosulfate, which is the thing that is removing the iodine, so it's not a reactant. What's not shown here is the hydrogen peroxide, and that's because if we mixed it all together at the start, it would all start reacting. So what's actually happening is everything in this table will be going in a flask. It doesn't matter how long I take to measure it all out because those things on their own aren't going to react. So in a separate test tube, I'm also going to measure out a particular volume, constant every time, of hydrogen peroxide. So why have we got different pieces of apparatus? Depends whether we're changing stuff or not, whether we're changing the volumes. So sulfuric acid is 25 centimetre cubed every time because that's a control variable. H2O2, 10 centimetre cubed every time, and thiosulfate, we want to keep the amount of thiosulfate the same because that's telling us how much iodine has been used up. So all of those ones that are staying the same, we're using a volumetric pipette, and that's because that's the most accurate piece of measuring equipment that we have. So if we only need to measure one volume, we're going to measure it accurately every single time. Then we've got our potassium iodide, which we're changing the volume of, and that's why we're using a burette. So a burette is the next best thing to measure small volumes. It's easier than using a measuring cylinder and it's more accurate. We're also adding water, and that's because we need to keep the volume constant. So the easiest way to change the concentration is not to make 5 separate concentrations of potassium iodide solution, but actually just to add different volumes of potassium iodide to different volumes of water in the flask, mixing it together. We've also got starch. really it says 1 centimetre cubed, but to be honest, the starch could be just a number of drops of solution, and because it's not so important, it's a very small volume and the concentration of starch doesn't matter really for the experiment. We're just using a squeezy pipette, Pasteur pipette or tea pipette, however you want to call it. Okay, so we're mixing everything together. We're adding distilled water. We've got everything in the flask except the peroxide, and then when we're ready to mix them together, we can start the stopwatch immediately. This is also helpful, this having two separate containers is also helpful if we wanted to change the temperature instead of concentration, because we can put both those containers in a water bath, allow them to come to temperature before we mix them together and start the reaction going. Okay, finally let's just have a look at how we might use the results of this experiment. So rate is proportional to 1 over time taken. We saw that in the disappearing cross experiment. So we can just do 1 over time, 1 over the number of seconds taken for it to go blue-black, and we can keep doing that all the way through. If we wanted to work out the moles of iodine, we could, because we know how many moles of thiosulfate we added. And then if we've got the total volume, we could work out the change in concentration. But it doesn't matter. 1 over time is always proportional to rate. So I can see how the rate is changing. And so the simplest possible way that we can analyse these results is simply to plot a graph of the volume of potassium iodide added against 1 over time, which is equivalent to the rate. And we get this graph here. So what if we wanted to plot concentration though? So what if we wanted to know, instead of volume of potassium iodide, what the concentration was, because this is quite a common experimental question in exams. So we need 3 pieces of information: the volume that we added, the total volume of the mixture, and the concentration that we started with. And our final concentration in a mixture, and this is so helpful in many different areas of chemistry, is equal to our initial concentration, like of the stock solution that we're adding, times by the initial volume, like the volume that we're going to add, and then divided by the total volume. That includes all the other things that we added to that reaction mixture, so the peroxide, the water, the all the different things. I've forgotten what else was in there, the acid. So final concentration, so if I was going to do that for the first experiment, well, the initial concentration is given as 0.1 in the table, and the initial volume was 5. If I go back and add up all the volumes in the previous table, actually ignoring the starch because it's probably less than 1 centimetre cubed, then it's going to be that 0.1 times 5, and the total volume of the whole experiment was 70. So I get a really small number, and I could do that for all of the rest of them. So is there a point in doing that? Well, if a question asks you, then yeah, the point is to get the marks in the question. When it comes to the graph, no, there is no point, because the concentration of potassium iodide is directly proportional to the volume that you add, because you keep the whole volume that you diluted. So you're dividing by the same number, 70 every time, you're timesing by the same number, 0.1 every time. So actually those numbers are directly proportional, and you're going to get the same shape of graph. And if we're finding orders, all we need to know is, when I change the concentration, what happens to the rate? Is it 0 first or second order? This graph shows me it's first order, no matter how I look at it, whether I do volume against time or I do concentration against 1 over time.